These are the answers to homework 1E. Here are part of the definitions that I would like you to know. And here are the rest of them. Now let's go on to the questions. Number 1, rank the following from weakest acid to strongest acid. These three acids here, HClO2, HClO3, HClO4, can be determined how strong they are by the ratio of oxygens to hydrogens. The more oxygens you have than hydrogens in the formula of the compound, the stronger the acid. HClO2 has only one more O than H, it's therefore a weak acid. HClO3 has two more O's than H's, it's therefore a strong acid. And because HClO4 has three more O's than H's, it's an even stronger acid, so these are ranked accordingly from weakest to strongest: HClO2, HClO3, HClO4. Question number 2. Rank the following from strongest base to weakest base. We're given Fe, OH taken 3 times, Fe, OH taken twice, NaOH. We've learned that the strong bases are the ionic compounds alkali metal hydroxides, or calcium strontium barium hydroxide. The third one here, NaOH, sodium hydroxide, is an alkali metal hydroxide, very soluble in water. It'll produce a lot of hydroxide ions in solution. It'll be the strongest base. The other two are not going to be strong bases, but to determine the strength relative to each of them, we've learned that the lower the charge of the metal ion, the more basic the hydroxide compound is, and the higher charge, the less basic it is. The middle compound, FeOH taken twice, contains an iron 2 ion, whereas the first compound contains a positive 3 ion. The lower the charge, the more basic the substance. So therefore, FeOH taken 3 times would be the least basic substance, and NaOH would be the most basic. Question number 3. Identify the acid, base, conjugate acid, and conjugate base for the following reaction. To determine the acid and base, we look at the reactants and determine which one is losing a hydrogen and which one is gaining a hydrogen. The Bronsted-Lowry definition of an acid is a substance that loses a hydrogen ion, and the definition of a Bronsted-Lowry base is a substance that gains a hydrogen ion. The C3H7NH2, going from reactant to product side, is gaining a hydrogen ion, it's therefore a base. CH3OH, going from the reactant to product side, is losing a hydrogen, it's therefore an acid. We've learned that bases, when they react, turn into conjugate acids, so C3H7NH3 positive must be the conjugate acid of the original base. And acids turn into conjugate bases, so CH3O minus must be the conjugate base of CH3OH. You can verify these are correct by looking at the reaction in the reverse direction and noticing the C3H7NH3 going from right to left is losing a hydrogen. That's what acids do. The CH3O minus going from right to left is gaining a hydrogen. That's what bases do. Number 4, identify the conjugate base for each of the following. Conjugate bases are what acids turn into when they follow the Bronsted-Lowry definition of an acid. That is something that loses a hydrogen ion. So if each of these acids loses a hydrogen ion, it turns into its conjugate base. If HF loses a hydrogen ion, it becomes F minus, that's its conjugate base. If water loses a hydrogen ion, it becomes OH minus, that's water's conjugate base. If ammonia loses a hydrogen ion, it becomes the amide ion, NH2 minus, that's its conjugate base. And if the bisulfate ion loses a hydrogen ion, it becomes the sulfate ion, that is its conjugate base. Number 5, identify the conjugate acid for each of the following. To identify conjugate acids, those are substances that are produced when a base follows along the definition of Bronsted and Lowry for a base. Bases are substances that gain hydrogen ions. So if a base gains a hydrogen ion, it's going to turn into its conjugate acid. If F minus gains a hydrogen ion, it will turn into the conjugate acid HF. If water acts as a base and gains a hydrogen ion, it will turn into H3O positive. If ammonia acts as a base, it'll actually gain a hydrogen and turn into NH4 positive. And if the bisulfate ion acts as a base, it will gain a hydrogen and turn into H2SO4. Number 6, for each acid, tell whether it is strong, weak, or non. Give its conjugate base, and then tell whether the conjugate base is strong, weak, or non. First one in number 6 is HiO3. This acid has 2 more O's than H's in its formula. It is therefore a strong acid. When it loses its hydrogen, it becomes the conjugate base, which is IO3-. And if the acid is strong, which means it loses 100% of its hydrogen ions, that means the IO3- will never gain a hydrogen ion, so it would be considered a non-base. B, HCN. When acids do not have oxygens in their formula, the only ones that are strong are HCl, HBr, and HI. This is therefore not one of the strong acids. It must therefore be a weak acid. When it loses its hydrogen ion, it turns into its conjugate base, which is Cn-. And if the acid is weak, which means only some of the hydrogens are released, that means Cn- would be weak as well because it could accept a few hydrogen ions, so it would be considered a weak conjugate base. C is HNO2 nitrous acid. It only has 1 more O than H in its formula, so that means that's a weak acid. If it loses a hydrogen ion, it becomes a conjugate base. That would be NO2-. And if the acid is weak, the conjugate base has to be weak as well. D, H3PO4. This has 4 O's and 3 H's. It only has 1 more O than H in its formula. That means phosphoric acid is a weak acid. The conjugate base is what you get when you lose a single hydrogen ion. So when 1 hydrogen ion is removed, you get H2PO4, and this should have a charge of only -1 because we've only lost 1 hydrogen. If the acid is weak, the conjugate has to be weak, so H2PO4- must be a weak conjugate base. Number 7, for each base, tell whether it is strong, weak, or non, give its conjugate acid, and tell whether the conjugate acid is strong, weak, or non. First one is NH3. The only bases that are strong are the alkali metal hydroxides, calcium, strontium, and barium hydroxide. So ammonia, although it's a common base, is not a strong base, it's weak. When a base gains a hydrogen ion, it turns into its conjugate acid, which would be NH4 positive. And if the base is weak, the conjugate has to be weak. B is NaOH. We've learned that this is one of the strong bases. It's an alkali metal hydroxide, so this is a strong base. The conjugate acid of this is what you're going to get if you just pull off the hydroxide and get a sodium ion, or if you think about the Bronsted-Lowry definition, adding a hydrogen ion to this, you would have the hydroxide turn into water, and you would have the hydrated sodium ion, NaH2O positive. Either of these would be acceptable for predicting what the conjugate acid is. If the base is strong, which means it 100% dissociates in water, that means the conjugate acid does not accept hydrogens or does not release hydrogens at all, so therefore it would be a non-conjugate acid. Number 8, for each change in pH, tell how the hydronium ion concentrations changed. Either say the hydronium concentration increases by a factor of blank, or the hydronium concentration decreases by a factor of blank. And 2, how the acidity has changed. Say either the acidity increases by a factor of blank, or the acidity decreases by a factor of blank. First one, the pH goes from 3.5 to 2.5. Anytime the pH goes down, the solution is becoming more acidic. Now, how much more acidic? We're going down 1 pH unit, and because pH is a logarithmic value, when you go down 1 unit, you're going down by a factor of 10 to the first. So we would say, as you decrease the pH, the hydronium concentration would increase by a factor of 10 to the first. So the solution has a concentration of hydronium ions 10 times higher if the pH goes down by 1 pH unit. And therefore, we would say the acidity increases by a factor of 10. The solution is 10 times more acidic. If in B, you have a pH of a solution go from 4 down to 1, it's becoming more acidic. That's 3 orders of magnitude difference because each pH unit, being a logarithmic value, is an exponent, power of 3 going down. So the hydronium ion concentration increases by a factor of 10 to the third, or 1,000. That means the acidity increases by a factor of 1,000 also. So a solution with a pH of 1 is 1,000 times more acidic than a solution with pH of 4 because it has 1,000 times more hydronium ions than the previous solution did. If we go from pH of 2.3 to 4.3, the pH is rising. That means the solution is becoming more basic. It's becoming less acidic, and it's becoming less acidic by 2 orders of magnitude. So that means the hydronium ion concentration decreases by a factor of 10 to the second, or decreases by a factor of 100. So we would say the acidity decreases by a factor of 100 as well. If the pH goes from 8 to 12, because it's rising, the solution is becoming more basic, or it's becoming less acidic. And because it's going up 4 pH units, it's decreasing its hydronium ion concentration by a factor of 4, or a factor of 10 to the fourth. So the hydronium ion concentration decreases by a factor of 10 to the fourth. So we would say the acidity decreases by a factor of 10 to the fourth as well. Question number 9, give the missing information for each of the following solutions at 25 degrees Celsius. Solution number 1, they tell you the hydronium ion concentration is 1.25 times 10 to the minus third. We have to calculate the hydroxide concentration, the pH, and the pOH. And this can be done in a variety of different ways, but I'm going to calculate the hydroxide concentration first with the relationship that for water solutions at 25 degrees Celsius, the hydronium concentration multiplied by the hydroxide concentration equals the Kw of 1.00 times 10 to the minus 14th. So using this expression, if I know the hydronium concentration, I can solve for the hydroxide concentration. That will equal 1.00 times 10 to the minus 14th, molarity squared, divided by the hydronium concentration of 1.25 times 10 to the minus third molar, and the 3 significant figures, this will give you the molarity of the hydroxides, 8.00 times 10 to the minus 12th molar. We can calculate the pH from the original hydronium concentration. That could have been done first. pH is just the negative log of whatever the hydronium concentration is. So you're going to take the negative log of 1.25 times 10 to the minus third. The molarity of hydroniums is a 3 significant figure number. So when we get our pH, it should be a 3 significant figure number. But you have to remember for pHs, because they're logarithmic numbers, the significant figures are digits past the decimal point. So the beginning 2 does not count as a significant figure. So 903 would make this a 3 significant figure pH. The last thing to calculate is the pOH, and if we use the relationship pH plus pOH has to equal 14.000, then I can solve for the pOH by going 14.000 minus the pH of the solution. And when we do this with both numbers accurate 3 places past the decimal point, I'll get a pOH of 11.097. In solution B, we're told the hydroxide concentration is 1.00 times 10 to the minus fifth. So to calculate all the other variables, and this can be done in a variety of different ways, but I'm going to first calculate the hydronium ion concentration with the expression at the very top of the slide. Kw equals hydronium concentration times hydroxide concentration. Solving for the hydronium concentration, it'll be 1.00 times 10 to the minus 14th molarity squared, divided by our hydroxide concentration that was given, 5.00 times 10 to the minus 5th molar, and this will come out a 3 significant figure number, 2.00 times 10 to the minus 10th molar. If we want to get the pH, we've just now calculated the hydronium ion molarity, so I'm going to take the negative log of 2.00 times 10 to the minus 10th. That's a 3 significant figure number. So now when I get my pH, I'm going to write that to 3 significant figures, which means because it's a logarithmic number, 3 places past the decimal point, so the pH comes out to be 9.699. The pOH is going to come from the relationship pH plus pOH equals 14.000. So solving for the pOH, I would go 14.000 minus 9.699, and that gives me a pOH for the solution of 4.301. In C, we're told that the pH of the solution is 4.50, and we want to calculate all the other variables. So the first thing I'm going to do is I'm going to calculate the hydronium ion concentration from the pH. If the pH is given as 4.50, then I'm going to take the antilog of negative 4.50 to get the hydronium ion concentration. Now, the pH 4.50 is a 2 significant figure number, right? Because pH is a logarithmic number and only the digits past the decimal point count as significant figures. So now when I calculate my hydronium concentration, which is a molarity, it's not a logarithmic number, I've got to write it to 2 significant figures in the normal fashion. So that would be 3.2 times 10 to the minus 5th molar. If I want to calculate the hydroxide concentration, that's going to equal the Kw, 1.00 times 10 to the minus 14th molarity squared, divided by my hydronium concentration using a guard digit, 3.16 times 10 to the minus 5th molar, and I get a hydroxide concentration of 3.2 times 10 to the minus 10th molar. The pOH then can be determined from the pH by going 14.000 minus the original pH of the solution. We could have actually done this first. And if we subtract those, because it's a subtraction problem and the 4.50 is only accurate 2 places past the decimal point, my answer will be rounded 2 places past the decimal point. That comes out 9.50. In D, we're given the pOH of a solution of 6.40. So if I know the pOH, I can calculate the hydroxide concentration from that by taking the antilog of the negative pOH. So the antilog of negative 6.40, which is a 2 significant figure number, will give me a molarity of hydroxide ions that's 2 significant figures. I get 4.0 times 10 to the minus 7th molar. If I want to calculate the hydronium concentration, I can use my hydroxide concentration that I just got and go Kw divided by the hydroxide concentration, keeping a guard digit so I'm not rounding twice in the problem. And that will give me a hydronium ion molarity of 2.5 times 10 to the minus 8th. If I know the pOH of the solution, I can calculate the pH by going 14.000 minus the pOH, which was given as 6.40. And this is going to be accurate 2 places past the decimal point. My pH of the solution turns out to be 7.60. Question number 10. The Kw for pure water at 60 degrees Celsius is 9.5 times 10 to the minus 14th. A, calculate the pH of pure water at 60 degrees Celsius. So the pH is going to come from the concentration or molarity of hydronium ions in pure water. And the only way you can get hydronium ions if you have pure water is if the water molecules bump into each other and auto-ionize to produce a hydronium and a hydroxide. So this is what's happening in pure water. This happens to be at a temperature of 60 degrees. So initially, all we have is water molecules. There aren't any hydroniums or hydroxides, but as some of the waters bump into each other, they will react. And we're going to form plus X of hydronium and plus X of hydroxide. So those will be the equilibrium molarities. The equilibrium constant expression for this reaction is hydronium ion multiplied by hydroxide ion equals the equilibrium constant, which is called the Kw. No denominator because water's a liquid and we don't put liquids or solids in equilibrium constant expressions. If we want to solve for the hydronium concentration and then eventually the pH, I'm going to use my Kw value of 9.5 times 10 to the minus 14th molarity squared at this particular temperature and plug in the equilibrium molarities of the hydroniums and hydroxides, very similar to what we've done in all of our equilibrium homework problems from the last chapter. Solving for X by taking the square root of both sides, X comes out 3.1 times 10 to the minus 7th molar, and this is the hydronium ion concentration of this particular solution of pure water at 60 degrees. If you want the pH, you're going to take the negative log of this number, so keeping a guard digit, I take the negative log of the 3.08 times 10 to the minus 7th. Now that's a 2 significant figure molarity, so I'm going to get a 2 significant figure logarithmic pH, which means 2 digits past the decimal point, so that'll be 6.51. So the pH of pure water at 60 degrees Celsius is 6.51. Part B says, is pure water at 60 degrees acidic, basic, or neutral? And if you said acidic, you are incorrect. Why is that? Because what we have here for pure water is we have equal amounts of hydronium ions and hydroxide ions, correct? The hydroniums were X, the hydroxides were X. They both equal 3.1 times 10 to the minus 7th. What's the definition of an acidic solution or a neutral solution or a basic solution? An acidic solution has a higher concentration of hydroniums and hydroxides. A basic solution has a higher concentration of hydroxides and hydroniums. A neutral solution has equal concentrations of the two. And as it happens at 60 degrees Celsius, then when you're at a pH of 6.51, that's when you have equal concentrations of the two different components. So therefore, this solution is neutral because the concentration of hydroniums and hydroxides are equal when the pH is 6.51. Number 11, organic acids, those acids containing a carbon atom backbone, also contain what chemical group? This is something we didn't talk about in the lecture, but it was in the chapter. Organic acids always contain, besides a chain of carbon atoms, an entity at the end of the molecule called a carboxyl group. It's a CO2H unit. It's a carbon double bonded to one O, single bonded to the other O, and that O is bonded to an H. And this is what makes organic compounds organic acids. An example of this would be acetic acid. We write its formula H, C2H3O2, but that really doesn't show how the atoms are bonded together. Acetic acid is actually bonded like this. Has the first carbon bonded to 3 hydrogens, then it has the second carbon double bonded to an O, single bonded to the other O, and that O is single bonded to an H. You can see the right side of this molecule is the carboxyl group CO2H. And it's these carboxyl groups that happen to have a very weak bond between the oxygen and the hydrogen. So this hydrogen, if it gets bumped into by a water molecule, can get pulled off, therefore making these types of materials acidic.